Thank you very much. I apologize for being the one person who disrupted the schedule and created all the confusion. So it says kilonovi on the schedule. That was yesterday's talk. Today I'm talking about tidal disruption events and specifically about this optical UV class that was just mentioned. So Stephanie said this theory was, this idea of tidal disruption events was predicted a long time ago, but I think really observationally it's really now is the very interesting time in recent years where a lot of progress is being made. And the basic predictions, as were mentioned, is this t to the minus 5/3 decline rate of the luminosity, which follows the predicted t to the minus 5/3 decline rate of the mass return rate to the black hole after the star is disrupted. The accretion disk is expected to emit in the soft X-rays. This is why the first searches were in these wavelengths. And the events are rare. So there's still about an order of magnitude discrepancy between theory and observations about what the event rate is, but it is either 1% or 0.1% of the supernova rate. So it is low. This is why we still have few events. Now, again, as Stephanie mentioned, the big discoveries, after the first tidal disruption events were discovered in the soft X-rays and kind of conformed to the theoretical predictions, there were two types of new events that were discovered that were not exactly as expected. So the first one, Swift J1644, was this high energy event. In the X-rays, there was no emission in the optical. The spectrum was non-thermal, and the X-ray had a lot of variability, and then maybe a t to the minus 5/3 decline. The other event published a year later was the first UV optical event. So kind of the opposite, lower energies than expected. It was thermal and it had a very smooth light curve. So since then, we have found more events of each class, and we kind of refer to it as the jetted TDEs or the high energy TDEs and the optical UV TDEs. And remember, these are on both sides of the energy scale from the soft X-ray TDEs, which are what was expected initially. So, initially in this plot I'm going to show now the interplay between theory and observation in this field in the last few years, right? Theory predicted you would get some soft X-rays from the accretion disk. Observations saw that, but now observations have seen a few more different things that were not initially predicted by theory. And so initially you would not think that these events are TDEs. And also why would they be so different, right? How can we get this huge variability? So the first idea was, maybe that's the difference between looking down the jet of the TDE versus looking off axis. So down the jet, you see this very high energy. Off axis, you see the optical. There is another idea to explain this difference, which I will get to later. But one way to test this idea are all of the optical events just off axis jets of the high energy events is to look in the radio. And so if there's, for certain assumptions about the jet and about the material around it, you should see radio emission even if you're looking off axis from the jet. And so here is the radio emission of that Swift event, which was seen on axis. And here are predictions for what the radio should be doing if you're looking further and further off axis. And here are all the non-detection limits from optical TDEs and a few weak detections. So by the fact that most of the optical TDEs are not detected in the radio, or those that are much weaker, it tells us that this is probably not an off-axis jet. This is probably some different mechanism that is responsible for these two classes of events. Okay, so what could it be? So here is the first optical event, the first optical UV event. So here's that smooth light curve going up and down. That's t to the minus 5/3. And the spectrum, which consists of, a host galaxy spectrum, a very hot black body, 30,000 degrees. And once you remove that, you're left with only two broad features of helium-2. So in first sight, this kind of looks like a supernova, but the peak magnitude of minus 20 is an area where we don't see many supernovae. It's brighter than most supernovae and fainter than most superluminous supernovae. The other thing was these features are not features we have ever seen in a supernova. Broad helium-2 lines and only broad helium-2 lines. It's not something we've seen before. And maybe most importantly is the temperature evolution. So supernovae can be also 30,000 degrees, but they cool very quickly within a few days. Whereas this event was 30,000 degrees for hundreds of days. It didn't cool, so it still had some heat going on there. Okay, and the other mystery, so this is not like any supernovae, but then here is the lack of hydrogen of this event, which is kind of strange because if you know, regardless of how this star is destroyed, supernova tidal disruption event, you expect to see the hydrogen. So it was not seen in this case. So here is the initial, to use Brad's terms, report card for this tidal disruption event as a tidal disruption event. You expect it to be in the center of the galaxy, and it was. You expect the luminosity to decline as t to the minus 5/3, and it was. But this is kind of where things get bad. You expected a temperature from the accretion disk and the soft X-rays, but the temperature was 1 or 2 orders of magnitude lower than that. You expect the tidal radius where the star gets disrupted is about 10 to the 13th centimeter for certain standard parameters. The thermal emission you get here has a black body radius of 2 orders of magnitude larger than that. And even if you just ignore all the details and just ask how much energy was released, 10% efficiency of throwing a sun into a black hole should give you about 10 to the 53 ergs. This was 2 orders of magnitude lower, just the total energy in the optical and UV. And you expect the temperature in an accretion disk to evolve. I don't know if you noticed in the light curve, all the colors were constant, so the temperature was constant. And you expect to see some hydrogen from the star being disrupted, and there wasn't any. Okay, so at first sight, there is really a lot of reasons to believe this was not a disruption event. And I think many of us were skeptical at the beginning. And so we wanted to look for more. We wanted to find more events. So here is that first event again, where it's the black body removed, that 30,000 degree slope removed. So you just see the features. So there's the no hydrogen and the broad helium-2. And so we looked, could we find more events? And we started the search with the Palomar Transient Factory, and we found a few new ones. So we found another event that was quite similar to the first one, no hydrogen and only helium. We found a few events that did have the helium and additional hydrogen. And this is a very interesting event that was already mentioned. This was from that search for the corona lines, these light echoes of TDEs, lone galaxies. And indeed, this was one of the ones found, these narrow lines are those kinds of corona lines you expect. But it also has underlying these broad features similar to the other events. So all of these events were discovered by transient surveys. This one was in the SDSS archive, discovered by looking for these corona lines, but also happens to have very similar broad features as the ones that were found in transient surveys. And it was actually found a year before what we consider the first one. So now we have this class, and they're all in galaxy centers. So this starts reinforcing the problem. And since this paper was published in 2014, we now have about 10 of these. So this is more or less the current picture. They are all in galaxy centers. They are all blue. They all have similar light curves except one, which is a little different. But most of them have these similar properties. So the first thing you can ask, the first theory of why there was no hydrogen was maybe that was the first thing in astronomy is always the rare one. So maybe the first one was this rare helium star that got disrupted. But now that a third of the events have no hydrogen, I think there needs to be another explanation for why there is no hydrogen, and I will get back to that later. It is probably a property of the radiative transfer in this system and not that the star itself didn't have any hydrogen, because a third would be too much if it were the properties of the disrupted star. Okay, so now that we have when we had about 6, and now we have about 10 of these events, all showing these problems, but all in galaxy centers, I think that caught the attention of the theorists that this discrepancy needs to be addressed. Why do the events look like this? Okay, so one idea was, when you do the simulations of these events, it's quite a messy problem, and you have a lot of material flying around. So even if you do form an accretion disk and it is emitting in soft X-rays, this emission will have to transfer through all of this material that is around the black hole, and maybe then it could change its properties on the way out. And some modeling by Nathan Roth and Dan Kaysen, indeed they inject the expected X-ray emission from the accretion, but they have it diffused through a radius of reprocessing material. They don't say what this material is, where it comes from, just assuming there is some spherical distribution of material. And then by changing the radius of this material, you can turn the hydrogen on and off and keep the helium pretty much constant, which is kind of what we see in the spectra, where we see all of them have helium-2 and some have hydrogen and some don't. So that's just a function of the outer radius of this material. And they also all have these very blue temperatures and are constant temperatures. So this is also a very promising explanation for what we see. However, there was an alternative explanation that Tzvi came up with, and this has to do with GR effects. So here you have two simulations of the star being disrupted by a black hole. The white circle is the black hole. This distorted thing is what used to be the star. On the left is what happens if you don't consider GR. It just orbits. The first models, thought that the squeezing that happens here at pericenter will produce these shocks that will be enough to dissipate energy, and the thing will circularize and form the accretion disk. But actually, the numerical simulations take a very long time to circularize. You see it slowly doing it, but in fact, they don't see it in the simulations until the end of the simulation. So there's actually a problem that, how do you lose the energy to circularize so that we get to see what we see? So when you do introduce GR, of course, the effect here is GR precession. And so the orbit precesses, and this is where you get these stream-stream collisions that Stephanie was alluding to. And that produces outer shocks. And these outer shocks are apparently much more effective at dissipating energy and allow the debris to circularize much faster. But also, this energy that is dissipated in the outer shocks will produce emission. And the first calculations by Tzvi on this emission were kind of matching the radii, temperatures, and timescales that we were seeing in the optical event. So suddenly we had to take a step back, and maybe all of the optical events we were seeing were not the accretion, but these stream collisions that happen as the debris is circularizing before the accretion happens. Okay, and this also prompted this explanation of the different, the variability between events, is that depending on how steep the star gets disrupted, so you can imagine a star is just grazing the tidal disruption event, and then the precession is pretty small, and you get these collisions pretty far out. But if a star goes very deep into the tidal disruption radius, then the precession is very strong, and you can get the collisions closer in, and this could cause these emissions to be in the X-ray. So maybe some of the diversity is all these outer shocks, these stream collisions happening in different parameters. Okay, so both the reprocessing picture and the stream collision picture explain the temperatures and the large radii, because now this is happening much further, emission is formed much further out. And also kind of explain some of the emission properties, the lines. But there's still this problem of the total energy. Where is the total energy going? Now, before I get to that, so when Tzvi first showed me this stream collision problem, my first thought was, okay, then if that's what we're seeing, then if we wait a little bit, we should see the accretion disk form after, right? How long will that take? Well, we didn't know. It could be a year. It could be several years. So we were monitoring the optical events in the X-ray, and recently we found one of these optical TDEs that here's the optical declining. So it's actually declining a little bit slower than t to the minus 5/3, but faster than exponential. And here's the X-ray rising by about a factor of 10 on that time scale. So maybe one interpretation of this is that indeed the optical is coming from the stream collisions outside, and that is dying down. As the accretion disk is being formed inside, the X-rays increase. So this looks like a confirmation of that picture. But I have already heard that the reprocessing material camp said that you can also get this from their picture. If the reprocessing material is dissipated, now you're slowly revealing the accretion disk that was there all along, and you're just seeing more of the X-rays come out as X-rays. So maybe this observation doesn't discern between the two models. Maybe it does. We'll have to see. The first numerical models of this actually showed that you get kind of both. You get the stream collisions, and from this collision you dissipate matter. So maybe this helps form some of that reprocessing material. So maybe it's actually some interplay between these two things. So we now actually have quite a bit of emission mechanisms that have been suggested. So the first picture, so this is overplot on the classical Reese picture of the star coming in and being disrupted, and half of the material coming back, and half of the material flying out. And so the initial picture was that, okay, we'll see X-rays from the accretion, but now we're saying maybe this accretion is reprocessed by some material. Maybe we're seeing emission from these collisions as the material comes back and collides with itself. And there is another mechanism, which is the other half of the star that we have so far neglected, that is flying out unbound, is hitting the ISM, and that will cause some emission as well. Okay, so now we were in a situation where observations had more stuff going on than theory, and now theory has caught up, but I think they overshot a little bit, and now there are more mechanisms in theory than we see in observations. Okay, but then there was the one event happened in 2014, the optical event that was the nearest one so far, so best studied, Assassin 14 Li. We saw all of this, we think. Okay, this is one interpretation. That we saw the optical UV from those outer shocks of the stream collisions. We saw the X-rays, either from the inner shocks or from the accretion disk being formed. And we saw radio, which in this paper is interpreted as the unbound material running into the ISM and producing radio. I should say there are two other interpretations of this same radio emission from different things. I will not have time to get into. But maybe we've seen all of this together now happen. Okay, so now, but what about the total energy? Where is this loss? So there have been some suggestions, maybe the efficiency is a little bit lower. Maybe it's not a solar mass. You can get a factor of a few if it's a smaller star. Maybe it's a partial disruption. Some people suggested, stars are not constant density. They have a core and an envelope. There is actually a tidal radius that is much more likely and because it's much larger for a star just to get its envelope disrupted. And that is a smaller mass. Another idea came again from Tzvi and their group that maybe it's due to elliptical accretion. So the standard picture where you need to lose the energy by circularizing is what is depicted here. So this is the energy versus the radius around the black hole for a different angular momenta. And so in the classical picture of circular accretion, you lose angular momentum and energy slowly, and then you can fall onto the black hole. In elliptical accretion, you can actually fall ballistically in and take that energy with you, and so the efficiency is much smaller. Okay, so this model has a great name. It's called the Jerusalem Bagel model. So there's Tzvi holding a Jerusalem bagel. So the bagels in Jerusalem are elliptical for some reason. And so this model came from Jerusalem. So this is the Jerusalem bagel model that explains where all the energy is going. Okay, so we all say that we want to study TDEs to learn about supermassive black holes, which is really the great ultimate goal. But I think we're still kind of in an intermediate stage where we're trying to understand what is going on and what is the correct accretion physics and radiation physics that we need to put together to understand the properties of these things. At least for the optical events that are not as was naively expected before. I think we still need we have a few missing steps to go from the properties of the TDE to the properties of the black hole. Okay, the other thing I want to talk about, it was a very surprising discovery about these optical TDEs. So when we found that first sample of 6 events that all were in galaxy centers, we looked, well, what kind of galaxies are they? So here are the spectra of the galaxies of those first 6 events, 7. And so this is the spectra of the galaxy over here, and this is just a zoom in on the blue part. So you see all of them except one are these quiescent galaxies, no emission line, not a lot of star formations. At first told us this is not some new type of supernova because there are no massive stars in these galaxies. But beyond that, these galaxies are peculiar in that they have these very pronounced Balmer absorption features that are typical of A stars. So these galaxies are known as E plus A stars because the spectrum looks like that of an elliptical galaxy plus this A star population, or post-Starburst. And the idea behind how you form a galaxy like this is you have a galaxy undergo some starburst event, so you form a lot of stars and then it suddenly stops. And then the massive stars die off, and if you wait a few 100 million years, the dominant population in the spectra is A stars. So the O and B stars die first, and then after a few 100 million years, you have A stars, and if you wait a little bit longer, it'll just be an elliptical. But somewhere there is this phase in between where it's not star forming, all the massive stars are died, it's still not an elliptical, you have this overpopulation of A stars that were formed in the starburst, and it's an E plus A galaxy. Now these galaxies are pretty rare. They're about a few % of galaxies in the field. So it was quite striking that almost all of the tidal disruption events that are optical tidal disruption events happen in these galaxies. I don't think we expected that. I should say the only one that is not an E plus A is the one that was discovered by looking for the emission line. So this was the one that was discovered by looking for the light echoes and happened to have those underlying broad features. That is not an E plus A, but all the other ones that were blindly searched for in transient surveys land on E plus A galaxies. Here's a way to see how crazy this is. This is a phase space of all galaxies in SDSS. So this is H alpha emission. So up here is star-forming galaxies. Down here is stars that aren't forming, galaxies that aren't forming stars. And this is H delta absorption. So again, over here, this is kind of an indicator of star formation history. So galaxies that were forming stars a few 100 million years ago are over here. So most galaxies go this way, and the starburst galaxies kind of go this way. And so there's a tiny little area here of phase space where all the E plus A galaxies live. But almost all of the tidal disruption events prefer this part. Okay, this is the one that was found by its emission line. So it was selected for having strong emission lines. And it is different, but all the other ones are down here. So for example, these three are, let's see, a third of the TDEs, but 0.2% of galaxies are here. So this is a 2 order of magnitude effect here, that TDEs prefer these galaxies. And then if you put Swift J1644, this first high energy TDE, totally different type of event, it also lands over here. So maybe there is a connection between these two events, these two types of events. Okay, so why are they in these galaxies? Okay, they can tell you we don't know yet. This is an open puzzle. What is special about these galaxies that make these transients so popular there? It also kind of makes the rate problem a lot worse, because if all of the ones we found are here, where are all of the ones in the normal galaxy? So we have some ideas that we are trying out. Could it be that there's a specific stellar population in these galaxies that is more easily disrupted when a galaxy goes in that phase? So for example, all these A stars that were created, maybe now they're all becoming giants. Giants are more easier to disrupt. Maybe, you just, when the galaxy goes through this phase, there's this epoch that it has a lot of giant A stars in the center, and they all get disrupted very quickly. So we try to age date how long from the starburst are these galaxies where the TDEs happen. And there are various techniques to do this. I will not get into it, but there isn't really a preferred single age for a single stellar population. So these are all the TDE host galaxies, and some of them are, okay, there's the one that is still forming stars, which is why it has a negative age. But all the other ones are around, a few 100 million years, and it's small number statistics, but there doesn't seem to be like a narrow preference for a certain stellar population that is just now evolving off the main sequence and being disrupted. So it doesn't seem to be something that's tied to a specific age very narrowly. Okay, so maybe it's a binary black hole. So if these galaxies are post-starburst galaxies, what caused that starburst? What caused it to start and suddenly stop? Maybe it was a merger. And indeed, many of these types of E plus A galaxies look like post-mergers. They have tidal tails, they have some dispersions. So maybe what caused the starburst was a merger, and if it was a merger between two galaxies, each with its own black hole, it takes a few 100 million years for the black holes to get together from the merger. And maybe what we're seeing is this time where the black holes are very close to each other, and when that happens, you get a spike in the TDE rate. So here are some n-body simulations showing the distance between the black holes in this plot, and then the TDE rate jumps when the black holes are the right distance. That happens a few 100 million years after the merger. So maybe these are all disruptions by binary black holes, and we're catching them right at this epoch when you expect a spike in the TDE rate. So there are a few problems with that too. This actually would not be enough. According to this simulation, this spike is very short-lived. It would not explain a 2 order of magnitude rate increase we see in the surveys. And also, if you try to guess what the mass ratio between the merger is, depending on the age of the starburst, you get that most of them are quite equal mass mergers. Whereas this spike rate in the events, in the tidal disruption events, doesn't really care about the mass ratio between the black holes. So if it doesn't care, you would expect most of the mergers to be, the more common ones, which are high mass ratio, and they aren't. So it's not clear if this can explain it. Okay, what about, so all of these post-starbursts have another quality, is that there used to be active nuclei that have shut down, or many of them look like this. So maybe these were active galaxies, they shut down, and there's some residual gas. And that is either what we're seeing is this gas being in and not the stars. or this gas is interacting with stars and increasing the TDE rate by these interactions. So in order to test this, we have an HST program where we're going to try and see if we can resolve, if there is some gas in the center of these galaxies. This will also allow us to age date them better and improve those plots I showed you to get better age dates since the merger, and to also see if these really are mergers. So these galaxies are pretty distant. HST should be able to see if there are any tidal tails or any signatures of merger. And finally, it should also tell us if the core of these galaxies is not symmetric. So all of the TDE rate calculations assume a symmetric potential in the center of the galaxy. But if these are disturbed galaxies, maybe it's not symmetric, and maybe that is somehow causing the rate of disruptions to rise. So the short answer is we don't know. We don't know why these galaxies are so popular with TDEs, but as an observer, we can exploit this fact. I told you we find the rate of TDEs is very low. We find very few of them. We only have about 10 in this sample of optical ones. Well, if they're all happening in E+A galaxies, and if those are only a few percent of the galaxies, all the wide field surveys running today are only going to have, a few percent of their galaxies are going to be these galaxies. Let's try and target them. Let's only observe E+A galaxies, and maybe then we'll find all the TDEs. So we started a project like this using the Las Cumbres Observatory, which I showed you yesterday. So you don't need a wide field telescope for this because you're targeting specific galaxies on the sky. You just need an efficient robotic telescope that can do that. And we've since upgraded to using the K telescope, which was one of the first supernova searches, actually the first robotic telescope searching for supernovae. And we've been monitoring 2,500 E+A galaxies for about a year now. This is still a small number because actually we don't know about many of these galaxies. They're quite rare. This is pretty much all of them in Sloan, which are nearby enough that we would see a TDE with this telescope. And so we're kind of now starting to be where we would expect to find the first TDE from this search. So we'll see what happens with that. If we don't find any, we will start putting an upper limit on this rate enhancement from there. OK. So that was the optical TDEs and their preference for host galaxies. I have a bonus part 3 of this talk, which is now that we have started looking for TDEs very closely, we started finding a bunch of other things that we don't know what they are. And so galaxy centers have traditionally been ignored by transient surveys in the optical because they are notoriously hard to deal with. When you look for a transient in a survey, you do image subtraction, and galaxy centers always subtract bad, so we always just mask them out. And also, if there would be something there, it'd probably be an AGN, and if not, 99% of the time it's a type 1a supernova, and those are already boring. So we're not paying attention to galaxy centers for a long time, but now we are, because we want to find TDEs. So we started now really systematically following every single transient that is found in the center of a galaxy. And we found some surprising things. Here's one of them. So this one is an assassin object, also called AT2017 BGT. Here's the first spectrum we got. At first sight, for those of you who don't know, it looks like an AGN spectrum. So you have hydrogen lines. You have the oxygen 3. So it looks like just another active galactic nucleus, nothing special. But it has this weird blue continuum, which is kind of unusual. And it has that double-peaked feature over there, which I did not recognize from AGN spectra. So I asked a friend of mine, Benny Trachtenbrot at the ETH in Zurich. He's an AGN specialist. Is that common for AGN? And he sent me back this plot, which is the blue spectrum is our spectrum, and the black is a composite of almost 700 quasars from SDSS. And you see that everything is identical except that none of them have that feature. Okay, so this was his way of saying, no, it's not common in AGN to have this feature. So what is that? So one of the lines is actually the famous helium-2 that we see in other TDEs. So is that a signature of a TDE, this helium thing? So at least according to one paper, the answer is yes. This paper came out last year saying, here's a TDE in a starburst galaxy. And implications if this is a TDE would be quite far because they only looked at 10 galaxies and found one of these. So if it were really a TDE, that means, we said the rate in post-starburst is high. The rate in actual starburst would be really high. But this is a similar spectrum to our event. It's a different event. You see this double-peaked feature over here, the helium-2. Same thing we saw. So in the paper, the justification for this being a TD is there's helium-2, hence it's a TD. But that is not entirely true, because here is that spectrum again compared to the UV optical TDs I showed you before. So it's true that they all have helium-2, but the line widths are completely different. So for the TDs that we've seen in this class before, the line widths are very broad, a few thousand kilometers per second. The helium-2 here is much narrower. Okay, so here's their event that they claimed as a TD, and here's our event. Again, this double-peaked feature here for helium-2 and something next to it. Okay, so the other thing that's strange about this event is that it's very long evolution time. So this is years. You know, the other teledisruption events I showed you go up and down in a few months. Here is their event, the Tad Hunter event. Here's our event with a similar spectrum and similar thing. The optical, UV, and X-ray, this does have a little bit of X-ray, are pretty constant. They are not changing on the time scales as the optical UV class I showed you before. Also, the spectra are not evolving. The other ones I showed you before, the spectra evolve with time. This is a year of spectrum, including one taken just a few weeks ago when this thing came back from behind the sun. All of the lines are still there, and they're not changing very much. Okay, so before this event was discovered, it was quiescent. We don't have a spectrum, but we know that the UV rose for some by a factor of 70, and now it's pretty much constant. Okay, so what is that? So I claim this is not necessarily a TDE signature. When you see helium-2, that doesn't automatically mean TDE, especially velocities are so different. So what could it be? Okay, so it turns out there's this radiative process that was predicted 30 years ago called Bowen fluorescence. Here's how it works. You need some hot ionizing UV emission source that will excite helium and then produce this Lyman, the equivalent of the Lyman alpha line for helium-2. That line then ionizes some oxygen line, and then that ionizes some N3 line. Okay, this is the process that was predicted to happen in AGN, and in fact was never observed. This is a paper from 1985 predicting that you should see O3 and N3 lines in these galaxies in addition to that helium-2 line. Okay, but it was not seen in broad line regions of AGN, so I think they kind of gave up and said this must be wrong. But if you look at our spectra, that's exactly what we see. Helium-2, N3, and here's the oxygen-3 line that is predicted by that process. Again, compared to normal quasars from SDSS, these are the features that are existent in our events and that are not seen in quasars before. Plus, remember, we had that blue continuum. So that is, there's some ionizing source under there. So maybe this is the first case of this Bowen fluorescence. So there is some blue, something which we don't know what it is, caused this blue flux to increase. That then did that whole cascade of lines that are the Bowen fluorescence, and now we see the helium, nitrogen, and oxygen line. And supposedly at some point when the UV fades, these lines should disappear. Okay, this is the test. So we now have this event. We have the one that was published as a TDE, and there's actually a third one, an OGLE event from the OGLE survey, and they all show this double-peaked feature. And so now we have 3 events, and that's how they compare to the class I showed you before. So much narrower lines, much slower evolution. So we think they are something else, but we don't know what. And now that we have 3, it's a class. So we have the 2 class of events. We don't know what it is. Okay, we think due to the time scales and the processes involved, it might be more related to AGN than TD, but it's not clear actually what the division between these two is in the first place, if it's very sharp or not. So I'll show you another event. This is another event. Again, the first spectrum is actually an event discovered by Gaia. We got this first spectrum. Looks exactly like an AGN. This time the features are all AGN-like. There's nothing special about the features. If you look at the Gaia light curve, you see that this galaxy was doing nothing and then suddenly had a factor of 10 increase in flux and is declining. So, you know, I don't know if we know how common this is for AGN to just have these kinds of outbursts. So this is something that has the spectrum of an AGN, but the light curve of a TD. Okay, so what is that? I'm happy to hear ideas. Here is another one. This one discovered by the Pan-STARRS survey. Again, spectrum looks like that of an AGN. Nothing very particular about it. I will just add that to confuse matters, this feature over here, which is on the wavelength of helium-2, is not helium-2, it's some iron line complex that AGN have. So that is normal for AGN, but then again the light curve doing nothing and then jumps by a factor of 10 in flux. And then if you zoom in on this part, in fact it went up and was flat and then went down. And this is actually kind of what you really expect from a TDE, because this level of being flat is around the Eddington limit that you expect for a supermassive black hole. So, you know, if I would just show you this light curve, you would say that's exactly what a TDE should do. Get bright when it reaches the Eddington limit, get flat, and, you know, and then decline later. But the spectrum is that of an AGN. Completely different than the ones I showed you before. So again, this diversity is just getting larger. I have to mention this event called Assassin 15LH because Ken mentioned it this morning. There is a dispute if this is the brightest superluminous, the most luminous superluminous supernova ever, or if it's something else. Okay, and we said maybe this is a TDE. So the spectra and the light curve, you'll notice, don't look like any of the TDEs I showed you, but they also don't look like any of the supernovae we know. So the advantage we have is that we are much more ignorant about TDEs than we are about supernovae, so there's more room for it to be a TDE than a supernova. But also we have other reasons to believe it's a TDE. For example, it's in the center of a very massive galaxy. Almost all superluminous supernovae are in small dwarf galaxies, and this one is totally different, and it's at the center. The problem is the galaxy is so massive that the supermassive black hole should be higher than the maximal mass where you expect to see a TDE. So remember, Stephanie showed you that at some mass, the stars just get swallowed whole. So this supermassive black hole in this galaxy should be greater than that. So how can we see a TDE? Well, you can get that if that supermassive black hole is spinning. Then the maximum mass goes up. So maybe this is the TDE around a rapidly rotating black hole, and there are some ideas of how that explains why it looks different than the other ones, and even how that might explain the rebrightening in the UV, which we have not seen in TDEs or in supernovae. Okay, so just to summarize, in the last few years we have discovered this class of blue broad helium-2 emitting optical TDEs with weird but common galaxy preference, or common amongst themselves, but that we don't understand. The emission sources of that class are still under debate. There's lots of room of a variety of phenomena from the outer shocks, from the accretion, from the interaction with the ISM. And now that we wanted to study those events more, we have run into this large diversity of events that we don't quite understand. So I think now we have beat theory, and there are now more events that theory can explain. But I'm a little afraid of what's coming next, judging by what has happened before. So we'll see where this goes. Okay, so how do we know if something is a TDE or an AGN? Is anything that doesn't conform to normal AGN behavior necessarily a TDE? How well do we actually know what normal AGN behavior is not clear to me. How would we distinguish what would be the smoking gun evidence to say this is a star that was disrupted and not gas falling in? So I think as an observer's point of view is what we really need to do now is start mapping this diversity, right? Every new event I showed you looked different. We need to start finding more and more of these and do some really systematic studies of what the observational phase space is. We have one class of 10 events, now one class of 3 events, and a few disparate ones. We need to fill in this region and see what the observational distribution of properties is, and hopefully that will help theorists come up with the models of what each group of these events really is and what its nature is. So I will be happy to take questions. Thank you.
Just want to speculate that every once in a while you'll have a system in which you'll have an accretion disk around this supermassive black hole, because it's a low luminosity AGN, which is not very active. But now when the star crosses it, this may cause an avalanche. Not in the first round, because the first time that the star crosses it, it will just cross it. But then, when the star is disrupted, it comes back as a stream. And when it comes back as a stream, then this matter from the stream is now sticks to the accretion disk. In a strange way, it also hits the accretion disk, supplying a lot of energy. So the whole accretion disk puffs. But eventually it goes, this material will go now on a time scale of few months into accrete rapidly onto the black hole. So this will look very, very different from tidal disruption event, which is happening around an isolated black hole. And it will look like something it will look like an AGN activity, because all that you have done is enhance the AGN activity for a period of several months. And you actually amplify the effect of the stellar mass, because you are causing much more mass to accrete, because you're causing also now disk mass, which was around it, to accrete. So this is my speculation for what you're possibly observing. And we actually have work on that, which hopefully will be published soon.
Okay, that's interesting. So I have a question for you. Would that suppress the normal TDE signatures we see in the other events that are around isolated black holes? Because it's not like we see the AGN on top of what we saw before as a TDE. So the spectrum does not have the broad lines. The evolution is different. So can you suppress that and generate the AGN-like emission?
It depends on the ratio of you have a large variety of activities. They're depending on the mass ratio of the disk of some ratio of the mass of the inner part of the disk to the mass of the disturbing star. And depending on this mass ratio, you can have very, very different activities, ranging from just a regular TDE as if the disk does not exist to an enhanced AGN activity with no classical TDE activity at all. So you can have both things depending on the different configuration.
Okay, so we are entering this regime now.
So in these theoretical models for these TDE events, do they use a Schwarzschild background or a Kerr background? I mean, is the black hole here rotating? And to what extent are the light curves dependent on the black hole spin?
So yeah, Tzvi can probably, and Stephanie speak much more to this than I can, but I would just say, generally, the light curves are dependent on the spin of the black hole. Some simulations have it, some don't have it. It's a very hard problem to model, from what I understand. The mass scales are very widely separated between the star and the black hole. The distance scales, where all the important stuff happens, are very widespread. So as far as I understand, a full dynamical GR with all the radiative transport in it and all the interaction between the things is currently beyond technical capabilities. Is that still correct? Or, yeah. So different models do different approximations to get around this. Either the mass ratio, or Stephanie said, only certain parts of the disruption. I would say, maybe to answer Thomas's question from before, maybe the biggest discrepancy is now there's no, I guess it's just not technically possible to model the whole thing self-consistently, with everything you need.
Do you think that any of the, what we would previously call helium-2 emission in like the optical UV TDEs is actually due to this Bowen blend? And does that tell us anything about why we see some of these nitrogen enhancements in a few UV spectra of these sources?
Yeah, that's a great question, which we had also asked ourselves. Let me see if I can find this figure again. So, yeah. So here, because the velocities are low, we know there are these two features, and we identified this. But what is going on over there? Could it be there and they're just blended? That's what you're asking? Yeah, I don't know. That's a good question. It could be there, because the profile of these TDE lines are kind of weird. So they could be hiding this process in them. We know the UV emission is there. We need to do we maybe need to do the modeling to see if that could work. But they could definitely be, not just helium-2, but a combination of ones for sure.